Hi, in this video I will solve exercise 6 and 7 from exercise sheet 4. So exercise 7. We need to prove that the function f of x equal exponential x is convex on R. Then we need to deduce that ex is greater or equal to 2 ex over 2 minus 1. Well, since we know that ex is differentiable, so all we need to do is to calculate f prime of x, which is ex, f double prime of x, which is ex as well. And since we know that this function is positive, then we deduce that f is convex on its domain of definition, so on R. So this is easy to prove that f is convex in R because f is differentiable. Of course, twice differentiable. Now, to prove the inequality, we know that since f is convex, then for all lambda and mu that belongs to 0, 1 with the condition that lambda plus mu is equal to 1, and for all x1 and x2 in the domain of definition of f, which is R, we have f of lambda x1 plus mu x2 less or equal than lambda f of x1 plus mu f of x2. So all we need to do now is to choose or to make the good choice of lambda and mu and x1 and x2 in order to have the inequality that they are asking for. So this is the tricky part in any question about convex functions. So if we want to use this inequality, we need to specify the lambda and mu and x1 and x2 in order to find what they are asking for. Now, they are asking for, we need to prove that ex is greater than 2 ex over 2 minus 1. Now, ex over 2 is the function f of x applied to x over 2. So it's f of something different than x. So if you want, it might be coming from here, because here we are modifying what's inside. I mean, we are replacing x by lambda x1 plus mu x2. In here, we have f of x1. So if our x1 is x, this would give f of x, not f of x over 2. That's why I will think about it as if the ex over 2 in here is coming from this part of the inequality. So I would say, I will try to put it in this part, and especially it's because ex over 2 is less or equal than the other part. So it's on this side of the inequality. So let me write it as ex over 2. So we need to prove this, which is equivalent to ex over 2 less or equal than half ex plus half, which, if we are trying to match to the inequality that we have due to the convexity of the function, we will choose then if we take x1 as being x, x2 as being 0, lambda as being half, and mu as being half. Then, if we write down the inequality, this one, we will have f of x is less than 1 over 2 f of x plus 1 over 2 f of 0, which means that ex over 2, it's f of half x in here, because it's lambda x, lambda x1, so it's ex over 2 less than half ex plus f of 0, it's e0, so it's 1, so plus half, which is the inequality that they are asking for. Now we need to prove that the function g of x given by ln of x is concave on 1 plus infinity. And then we need to deduce that we have the given inequality. So first, to prove that it's concave, also we know that the function is differentiable, so let's calculate the second derivative. So g prime of x is equal to the derivative of what's inside, so ln of x, which is 1 over x, over ln of x. so it's equal to 1 over x ln of x. Then g double prime of x is equal to u prime v minus v prime u over v squared, so it's x ln of x times 0, this is u prime v, minus v prime u, so it's the derivative of x ln of x times 1. The derivative of x ln of x, it's ln of x plus 1, everybody over x ln of x squared, so it's equal to minus ln of x plus 1 over x ln of x squared. So for x belonging to 1 plus infinity, ln of x is positive, so ln of x times x squared is positive, of course, so all the ratio is negative. Since it's negative, then g of x is concave on 1 plus infinity. Now we need to prove that ln of x1 plus x2 over 2 is greater or equal than square root of ln of x1 times ln of x2 for all x1, x2 greater strictly than 1. Of course, you know that since f is concave, or it's g in this case, since g is concave, then for all lambda mu that we choose such that lambda plus mu equals to 1, we have g of lambda x1 plus mu x2 for any x1, x2 in the domain of differential of g is greater than lambda g of x1 plus mu g of x2. Now we will try to match this to the inequality that they are looking for. So we need to make the good choice of x1, x2, lambda and u to find what they are looking for. So it seems that if we choose lambda and mu equals to half each one of them, then x1 being equal to x1 and x2 being equal to x2, we will have something like ln of x1 plus x2 over 2, which is something similar to what they are looking for. So let's try it. Choosing x1 equals to x1. So in here we by accident in the exercise it's x1 and x2, and in here it's x1 and x2, but it should be here, or it might be x and y. Okay, so we choose x and y as being x1 and x2, and y1 being equal to y1, and we choose lambda equals to half and mu equals to half. Then, so this is something that we know because g is concave. So we choose this and we replace in this inequality, then we will have ln of half x1 plus half x2, so x1 plus x2 over 2 greater than half ln of x1 plus half of ln of x2, which means that it's greater than ln of x1 to the power half plus ln of x2 to the power half, which means that it's greater than, because ln of a plus ln of b, it's ln of a times b, so it's greater than ln of square root of ln of x1 times ln of x2. And since the function ln is increasing, then ln of something greater than ln of another thing, then since ln is increasing, we have ln of x1 plus x2 over 2, so what's inside in here is greater to what's inside in here, so greater to square root of ln of x1 times ln of x2, which is the inequality that they are asking for. Now for exercise 6, the first one, we need to find an upper bound of the approximation of the error between, of the error committed when we approximate the square root of 10001 by 100. So we need to find an upper bound of the difference between square root 10001 and 100. So we need to find this difference using the mean value theorem. So it's natural to say that, okay, if we want to use the mean value theorem on the function f, so f is continuous, f is differentiable, on which interval? It's continuous on 10,000s and 10,001, and differentiable on the open interval. Then, using the mean value theorem, there exists C that belongs to this interval such that f of p minus f of a over b minus a, which is 1 in this case, is equal to f prime at the point C. So this translates into square root of 10,001 minus 100 over 1 being equal to the derivative of the function square root of x. So it's 1 over 2 square root of x at a point C. Okay? Well, we know that C is between 10,000 and 10,001. Then, if we calculate the square root and then we multiply by 2 and then we calculate the inverse, we will have 1 over 2 radical of C is between. So first we calculate the square root, then by 2, then the inverse. So it's less than 1 over 2 square root of 10,000 and greater than 1 over 2 square root of 10,001. So this is equal on this side to 1 over 200. Therefore, then the difference between square root of 10,001 and 100 is less than 1 over 200, which is an upper bound of the error between square root of 10,000 and 100. On another side, it's greater than do this. So it's greater than 1 over 2 radical of 10,001. So when we need to calculate the error, we need to find the maximal difference, whether it's negative or positive. Okay, so we don't care if it's positive or negative. But the biggest difference that might occur in this approximation is this one, because it's greater than this one. So since we have these two inequalities, then we can say for sure that the absolute value of the difference, which is the maximal error that might occur, it's less than, one second, be careful here, it's sticked. So it's less than the biggest one of these two terms, so it's less than 1 over 200. Now, in question B, they are asking about the approximation between cosine 1 and half. So we need to find the difference, or an approximation of the difference between cosine 1 and half, the difference. So it's between cosine 1 and cosine pi over 3. So take the function g of x being equal to cosine x. Cosine x is continuous on 1 pi over 3. Cosine x is differentiable on 1 pi over 3. Then mean value theorem says that there exists C that belongs to 1 pi over 3 such that cosine pi over 3 minus cosine 1 over pi over 3 minus 1 equal to the derivative of cosine at the point C, so it will be minus sine C. So cosine 1 minus half is equal to pi over 3 minus 1 times sine C. Well, we know that C is between 1 and pi over 3. Since sine is an increasing function between 0 and pi over 2, it means that sine 1 is less than sine C less than sine pi over 3. So pi over 3 minus 1 sine 1, this is a positive number, pi over 3 minus 1, less than pi over 3 minus 1 times sine C, less than pi over 3 minus 1 sine pi over 3, which means that cosine 1 minus half is between pi over 3 minus 1 times sine pi over 3, so which is radical 3 over 2, and pi over 3 minus 1 sine 1. So since this number is greater than this number and both are positive, then the difference cosine 1 minus half is less than pi over 3 minus 1 radical 3 over 2, which is the upper bound of the error when approximating cosine 1 minus half. We take this number and not pi over 3 minus 1 sine 1 because it's the biggest number, so it's the worst case scenario.